Hello and welcome to this video on the mechanical neural network, the MNN. In this video we will do two things. We will first have a look at this mechanical neural network and what it can do, and later we will then have an example where we try to solve the famous XOR problem with the network. So what do we see here? We see a multi-layer perceptron with 3 layers, one input layer here with 2 neurons. These 2 levers here are 2 neurons. Then we have a hidden layer here in the middle with 1, 2, 3, 4 neurons. And then here in the end we have the output layer with 2 neurons, 1 and 2. So as I said, we have levers which represent the neurons, and we can move these levers up or down. So this would be the input neuron number 1, this would be input neuron number 2. If we move it into this position, this would correspond to a 1. Moving them in the horizontal position would correspond to 0, and then moving them counterclockwise, this would correspond to a negative input of -1. Then we want, of course, to connect somehow our input to our hidden and then our hidden to our output neurons. And to do that, we have these strings here and here, which are basically the connections. If you look here at the top, this would basically be the graph. If you would find a graph of this neural network, then you would end up with exactly this structure here, where we have the 4 outgoing strings or connections to all the 4 neurons in the hidden layer, and the same here for the other input neuron. And then here for the connections from hidden to output, we have this connections from each of the 4 hidden neurons to each of the 2 output neurons. So these are our connections from the neurons, from the layers. So we have a fully connected network, of course, where each neuron from one layer is connected to all neurons in the next layer. And of course, one thing we want to do is we want to weight connections. So at the moment, as you can see, nothing is happening here in the hidden layer. So we want to weight the connections, and we do that by taking out these clamps and moving them on the lever. And now if we see and observe here the neuron in the second layer, we see that it is moving as well. So now we set basically the connection from the first neuron in the first layer to the first neuron in the second layer to 1. And we can also do the same thing, put it over here, fix this no problem. And now we have a negative connection, so if we activate this neuron here, nothing is happening here. Why is that? That's because we have, of course, activation functions. We need to have the nonlinearity in the multi-layer perceptron, as we would have just a single perceptron, basically. So the activation function, which is used here in this model, is the rectified linear unit activation function. Basically, it prevents the neuron to produce negative output. We can have only positive output. This is linear to the input of the neuron, and for negative input, the neuron would output 0. And this is exactly what's happening. If we here have a negative input, the neuron stays neutral. If we would now have a positive input, then this exactly mimics the input from the previous. And why is this happening? This is happening just because of this bar here. So this is a very simple contraption preventing the neuron from rotating counterclockwise, which would relate to a negative output. So we have the activation functions. We said how we can set our weights. One thing which is missing here is how we add the different inputs. So by now we had only one input to our neuron here, to our hidden neuron here. And let's say we have 2 inputs, for example, from the second input neuron as well. And what's happening now is, if we move the 1, for example, then we see the neuron is going up. If we now move the other one down, for example, then we see this neuron is coming down again. So these two are now weighted against each other, and this is simply done by this pulley system here. So we have one pulley where the two inputs are coming in, and here the output, the weighted sum of the two inputs is put out. We connect here in the middle between the center or the fulcrum of this lever and the most outside point, because we have this pulley here which basically halves the distance which it is traveling, and therefore we account for that by coming here in the middle. And we do the same here. Here we have 4 inputs for this output neuron, so we need this double pulley system which sums our 4 inputs together to one weighted sum, and we come here at 1/4 of the distance because the movement here is divided by 4 because of this double pulley system. So that's basically the mechanical neural network. We can basically model a multilayer perceptron with rectified linear units as activation functions. We have the summing of the inputs, we have the weighting of the inputs, we have activation functions, everything is there. So of course we can solve a problem with it, which we can also solve with MLP. And one famous example would be the exclusive OR the XOR problem, where we want the output to be 1 only if one of the input neurons is 1. If both input neurons are 0 or both input units are 1, then we want to output 0. So for that we need only the 2 input units or input neurons, these 2 hidden neurons, and this output neuron here. And let's try and build from scratch what we may need. We start with that. So we said when we activate this neuron, for example, we want an output of 1. So let's do this. Okay, now we come to here. Then we have to propagate this basically to here, so we can set this connecting weight to 1 as well. And now this looks quite good. We can activate here, and we get an output of 1 as well. This is nice. Okay, for here it doesn't work. So we have to do the same thing as well. Naively, we could do it just for the same neuron. So do it like that. So now I can put here. So I connected this second input neuron also to the first hidden neuron. We get an output here, an output here. Have 0 if we have no input. But if we now move both up, well, we get an 1 as well. This is not what we want. So maybe what we can do is use a second hidden neuron. So let's connect our second input neuron to our second hidden neuron. And also, of course, we need to connect our second hidden neuron to the output. So again, let's check. It looks good. That looks good as well. Let's try both together. Well, it still doesn't work. Why does it not work? Well, we need to somehow inhibit that both of these get activated. And one way we can do this is by setting, for example, this weight to -1. So now this neuron inhibits the movement of this neuron. So if I activate this now, this gets activated by this neuron. And if I activate now this as well, then this thing here gets deactivated. This looks good, but now this is also active. And we want the output to be 0, of course. So we do the same inhibition again in the other way. So it's basically a nice symmetrical problem. We do it like that. And now we have both inputs active. The output is 0, that's what we want. We can set both inputs to 0. Output is still 0. We set one of the inputs to 1. Output is 1. Check for the other input to 1. Output is 1 as well. So basically we are now done. We solved our XOR problem by using the weights and the inhibition and the symmetry. So basically this neuron gets active by this input, but gets inhibited by this input, and this hidden layer or hidden neuron gets inhibited by this input and activated here by the second input. And if we take a closer look at this pulley, we can basically see if we move them simultaneously, these pulleys do not go up or down, just the string is moving through them. So the two inputs are basically weighted against each other. Okay, I think this is enough for this short presentation. Thanks for watching and see you next time.